The discovery of exoplanets and the science of how they are found is truly fascinating. Exoplanets could be the key to questions that have continuously puzzled us for centuries, like, is there life on other planets? That is why one of the key missions of the James Webb Space Telescope is to find exoplanets with the potential for life. Only a few weeks into 2023, and JWST did just that. Join us as we uncover the mysteries of exoplanets with the James Webb Telescope and its newfound Earth-like exoplanet that has the potential for supporting life as we know it. The subject of exoplanets is simply incredible, with their ancient secrets waiting to be revealed and the promise of a world beyond our own solar system. It's easy to see why the James Webb Telescope was sent into space to search for them. Since its initial unfolding in space, JWST has helped us gather so much information about the age of our universe and how the universe works. And now, it has exposed an exoplanet that is pretty much the same size as Earth and is found within a habitable zone. JWST is the most powerful telescope ever sent into space. Unlike Hubble, which has spent its career orbiting the Earth, JWST actually orbits the Sun at a distance of 1.5 million kilometers or 100 million miles away from Earth. As you might imagine, the most advanced space telescope of all time definitely requires a group effort in order to keep it operating at its best. Webb is a multinational collaboration involving the Canadian Space Agency, the European Space Agency, and NASA. The James Webb Telescope was launched on Christmas Day in 2021 and is meant to act as our observer in the sky, peering deeply into space, looking for areas of interest. In fact, JWST is focused on investigating 4 main topics in particular: the earliest light in the universe, the creation of galaxies in the early universe, the birth of stars and protoplanetary systems, and planets in general, which includes the search for life outside of Earth. JWST is fitted with the latest and best spectrometers, cameras, and other instruments that allow it to precisely measure the things around it, things like stars and planets. JWST has a near-infrared camera, or NIRCam, a near-infrared spectrograph, or NIRSpec, a mid-range infrared instrument, or MIRI, and a fine guidance sensor, near-infrared imager, and slitless spectrograph. Good luck pronouncing that acronym. These instruments allow JWST to observe long infrared wavelengths of light not previously detectable by other space telescopes, allowing us to make new inferences about the age, structure, and evolution of the early universe. These instruments are also essential for spotting and analyzing planets outside of our solar system. JWST has certainly paved the way for a new generation of space discovery, not least of which includes the newly confirmed exoplanet LHS 475b. LHS 475b doesn't exactly roll off the tongue, does it? How did it get that name? LHS 475b is so named because it is the first planet to be discovered around the star LHS 475. According to the Exoplanet naming convention, the star of a newly found system is the implied A of that system, and each subsequent planet that we discover orbiting around that particular A star gets assigned the next letter in the alphabet, in this case, B. The LHS 475 part is simply a reference number straight out of a star catalog. The LHS 475 system is relatively close to Earth in cosmology terms. It's only about 41 light-years away and can be found in the constellation of Octans in the southern hemisphere. LHS 475 is a red dwarf star, meaning it's not as large nor as hot as our Sun. If our Sun comes in around 5,600 degrees Celsius, about 10,000 degrees Fahrenheit, then the average red dwarf star is closer to 3,500 degrees Celsius or about 6,300 degrees Fahrenheit. This cooler temperature and dimmer appearance make it impossible to see red dwarf stars with the naked eye, let alone the planets that orbit around them. But no exoplanet gets past JWST, or TESS for that matter. TESS? Yes, TESS. While JWST observed a dip in the LHS 475's brightness for about 40 minutes, confirming the presence of a planet orbiting the star, it was TESS that told JWST where to look in the first place. TESS is the Transiting Exoplanet Survey satellite, which monitors the brightness of up to 200,000 of the brightest stars in the sky. TESS does this by splitting the sky into 26 sectors and staring at each sector for 27 days straight. During that time, TESS monitors the brightness of the stars within that sector, looking for any drops in brightness. If it detects a drop, that's a strong indication of the presence of a planet and definitely worth investigating further. Sound familiar? That's because TESS operates much like its predecessor, the Kepler Space Telescope. Except TESS surveys an area 400 times larger than Kepler ever did. Kepler was the originator who opened our eyes to the diversity of the planets that exist in our universe. With more than 2,600 newly discovered planets to its name, the Kepler telescope set a new precedent for space exploration. And now TESS and JWST are only too happy to rise to the occasion and even over-deliver. While TESS is great at capturing changes in the brightness of a star, a dip in brightness doesn't always mean the presence of an exoplanet. There are several other reasons why the brightness of a star might dip. They can be caused by a telescope or processing malfunction. Dips can also result from star spots, which are a lot like sunspots, except they happen on other stars. And then some stars just have built-in variability that causes them to dim once in a while, all on their own. So then, what type of dip in brightness do we need to see in order to confirm it's an exoplanet? If the star in question has planets, and one or more of them orbits the star in a way that causes it to pass directly in front of the star as seen from Earth, then it is said to have done what astronomers call a transit. When this happens, the planet doesn't just automatically get some sexy exoplanet moniker. Instead, it gets cataloged. Astronomers call it a TOI, or a TESS Object of Interest. The newest TOI is then added to a huge database along with all the other previously recorded TOIs. And from there, scientists determine which TOIs are most important and relevant to focus in on. Currently, scientists are focused on learning about planets that orbit dwarf stars, because smaller stars mean even smaller planets orbiting them. These smaller planets are more likely to be rocky in nature, which means they are a great place to search for Earth-like planets with an atmosphere that potentially supports life. These small rocky planets are also more likely to be orbiting close to their parent star. If they're close enough, they're in what is called the habitable or Goldilocks zone, because they are in an area that is just right for supporting life. The other great thing about planets orbiting their parent star so closely is that they also tend to orbit them quickly. These relatively fast orbits make it easier for JWST to observe their transits, sometimes even more than one transit during a single observation window. This is precisely what happened with TOI 910.01. aka the earlier mentioned LHS 475b. The naming conventions are certainly not getting any less confusing. Scientists officially confirmed this object of interest to be a planet after observing 2 transits around its red dwarf parent star. The first transit was observed on August 31st, 2022, and the second was observed 5 days later on September 4th, using JWST's near-spec or near-infrared spectrograph. By taking the data from JWST and fitting it to a model of a planet orbiting a star, scientists were able to confirm certain information about LHS 475b. Firstly, this planet takes only 2 Earth days to orbit its star, which means an entire year on this planet is only 2 Earth days. They have also determined that this planet is almost exactly the same size as our own, with just a slightly smaller mass. So undoubtedly, LHS 475b is very Earth-like. But only 2 days for an entire year? Talk about time flying. Due to the nature of its orbit, LHS 475b is thought to be tidally locked to its parent star, meaning that one side of the planet always faces the star. From the perspective of LHS 475b then, one of its days, the amount of time it takes for it to rotate on its own axis, is exactly the same as one of its years, the amount of time it takes to orbit around its star. Not very Earth-like. On Earth, that would be like if one half of the planet only ever experienced daytime, while the other half of the planet was perpetually shrouded in darkness. But back to LHS 475b. If one side of the planet is constantly facing its star, does that mean that half is completely scorched? Well, despite being the closest planet to its star, remember that LHS 475 is a red dwarf star, meaning its temperature is less than half that of our Sun. So maybe LHS 475b is not as burnt as you might initially think. The goal of studying exoplanets is primarily to study their atmospheres. Are their atmospheres stable enough to foster life? Or, since most of these planets are tidally locked, do their atmospheres just boil away completely? To determine the atmospheres of exoplanets, scientists use data from, yes, you guessed it, JWST. The transmission spectrum is the only means we presently have to assess an exoplanet's atmosphere with any degree of precision. And JWST's spectrometry capability enables it to interpret this transmission spectrum like a pro. The transmission spectrum typically involves looking at how light changes before and after transit, with the difference giving details on the impact of a planet's atmosphere. The results from the collected data are still a bit unclear. There is some chance that LHS 475b has a watery or Earth-like atmosphere. But the more probable interpretation of the data currently points to it having no atmosphere at all. This means that, unfortunately, the atmosphere of LHS 475b has probably been boiled off by its parent star. However, it is important to note that the great JWST did not throw its full technological capacity at this round of transit observations. So another possible interpretation from the limited data we have is that LHS 475b might also have a very thick atmosphere with lots of clouds, very similar to Venus or Titan. Thick cloud coverage will limit how much light from the parent star is able to pass through the atmosphere of the planet in order to even be detected by the near-spec aboard JWST. So as of right now, the data is still insufficient to determine what kind of atmosphere exists on this planet. So what do we do? Fortunately, a third transit of LHS 475b is scheduled for summer 2023. This is super exciting because more transits mean more data and more definitive answers. Scientists will observe this third scheduled transit with the help of MIRI, the Mid-Infrared Instrument, another handy-dandy tool on board JWST. MIRI will be able to easily settle this dispute of whether LHS 475b has an atmosphere of thick clouds or practically no atmosphere at all. MIRI does this by detecting temperature. Simply enough, a planet with a dense atmosphere will be hotter than one with no atmosphere. While we wait for the answer, it's fun to imagine that we might have just discovered a second, slightly warmer Earth only 41 light-years away. Regardless of the results, JWST, with the help of TESS, is proving revolutionary in the search for and analysis of exoplanets. LHS 475b is just the first. Think of the thousands of exoplanets yet to be discovered. Do you think that studying exoplanets will directly result in us finding a new Earth? Let us know what you think in the comments.